All right, welcome everybody. Today we're going to be talking about section 13.1. Our objectives here today are to write dissociation equations, to write total ionic equations for reactions that are in aqueous solutions, and to identify spectator ions and write net ionic equations. So these things that we're doing today are basically a way to rewrite equations to help us understand what's happening to the ions. Okay, so when you get out of here today, your criteria for success should be, if I give you an ionic compound, you would be able to write a dissociation equation to represent how the ions are going to separate when the compound dissolves. That's going to be really easy, okay? It's an easy part of this. Next, given a precipitation reaction, you can use solubility rules to determine which products will be soluble and which products will precipitate. Remember, precipitate means that it's coming out of solution as a solid. And so you're going to have to use a chart, and you're just going to need to be able to interpret and read a chart for this particular part of the lecture. And then finally, to represent precipitation reactions with total and net ionic equations. We're going to show you these net ionic equations. They are not difficult, but they are detailed. So as I'm going through this material, make sure that you're paying attention to the details here, because they're not hard, but they are detail-oriented. All right, so first of all, let's talk about what dissociation is. Now, interestingly enough, we use this phrase dissociation to talk about when ions are separated out and spread out in a solution. So we talked about solvation before, and we talked about the idea that if you take a chlorine ion and surround it by water, these are the green ones here, right? And then you take the sodium ions, and those are the purple ones, you surround them by water, that's called solvation. Well, if we're doing it in terms of ionic compounds, we call it dissociation. Ironically enough, it might kind of seem weird. I mean, it makes sense, but it also seems kind of weird. When you do this with molecular compounds, you call it ionization. Ionization. So it's kind of weird, but dissociation is when you're breaking apart ionic compounds. Ionization is when you're breaking apart molecular compounds that are then forming ions. So dissociation, you already have ions, and they're just basically breaking apart into smaller pieces surrounded by water. Okay. When you do it with molecular compounds, we'll cover that at the very end, then you're doing it with a substance that's normally a molecule, but then it actually breaks into an ion, and so you call it ionization because you're forming a new ion. So what we want to do is we just want to represent what's happening here. We want to show that when you start with sodium chloride as a solid, okay, that little S down at the bottom of sodium chloride, remember, means solid, then it breaks apart into the sodium ion and the chlorine ion. Again, remember, we want to make sure that we're pointing out here that you've got the ionic charges here. Also notice that I put an AQ after each of these, and that's to indicate that I now have an aqueous solution. Okay, that in other words, these things are surrounded by water. So the sodium ions and the chlorine ions are in a water solution now. They're not as part of the crystal anymore. If they were part of the crystal, we would say that that's the S, right? These are all part of the S. But all of these over here are all the AQs. Okay, these are all the AQs because they're surrounded by water. Okay, the crystal is the S. The AQs are all the parts that are surrounded by water. Okay, so that is what you would do to represent dissociation, right? Not hard. We just have to take the thing that was the solid, the crystal, and we break it into its two components. Okay. Now, it's important to remember where these charges are coming from. I just wanted to remind you about that really quick. Remember, when we look at the periodic table, we have the different groups, right, on the periodic table. And so we had group 1 and group 2. Then we had this little gap. We had group 13 then came over here, right? We had the groups 13, 14, 15, 16, 17, and 18. Remember that anything in group 1 has a +1 charge, group 2 has a +2 charge, group 13 has a +3 charge. Remember those? And then we had remember noble gases in group 18 that were 0, group 17 had a -1 charge, group 16 have a -2 charge, 15 had -3. Remember those different little things we learned last semester, right? So don't forget that. When you're trying to figure out what these dissociated ions are going to be, what the charge is, you have to go back to what we learned first semester with those. Okay, so your turn. Write dissociation equations to represent what happens to each of the following compounds as they dissolve. So I've got Na2CO3. Okay, now I'm going to go ahead and show you a couple of these, and then we'll let you practice one here in a second. This one is sodium carbonate. Now notice the 2 here and the 3 here. Now notice what's going to happen as I go to this next part, to that 2 into the 3. This 2 that was a subscript now became a coefficient, but that 3 did not become a coefficient. It just stayed a subscript. Don't forget that you have to pay attention to polyatomic ions here. Now, it's been a while since we've had to talk about polyatomic ions. In your book, they're on page 214, if you're trying to remember where they came from, if you want to look at them again. Remind yourself what these things are, because when you see them, it can kind of get confusing if you don't remember, hey, this is a group. These guys all stay together. And so that 3 doesn't need to come out in front of my oxygen and say I have 3 oxygens. The carbonate, remember that carbonate is basically the combination of carbon and 3 oxygens. And together they have a charge of -2, right? So we can say together that that's carbonate with a -2 charge, and we don't have to take that 3 and put it out in front of anything there, okay? All right, so let's look at another one. If we look at this next one, we see that we've got magnesium and chlorine. Now, one of the things that was not included up in this one up here, which we always really need to include, is the AQs, all right? Don't forget to have AQs on that sodium and that carbonate, because you're saying, hey, these are surrounded by water. Now, this magnesium and chlorine, think about what's going to happen. I've got magnesium. Now, what's the charge, right? Don't forget about putting a charge there. That's important. There's no number after it, so I don't need a coefficient here. But it is dissolved in water, so I need to have an AQ. My chlorine does have a number out here, a subscript. I have to ask myself, does that become a coefficient in front of my chlorine? Yeah, actually it does, right? It becomes that 2 out in front of the chlorine, and the chlorine has -1 charge. Now, the magnesium has a +2 charge. Why? Because it's in the second group. It's in group 2 on the periodic table, so it gets a +2 charge, meaning that it's giving 2 electrons away. Don't forget that what's happening here is that I've got magnesium, it's got 2 extra electrons, and it's basically giving one of its extra electrons away to one chlorine and another one of its electrons away to another chlorine, right? And that's what makes them attracted to each other. This now has a 2 positive charge, each is a negative, and so there's an attraction to that, to each other because of those opposite charges, right? And so that's what's happening when we're doing this. Just need a little bit of reminder, I bet, to keep that in mind there. All right, so let's look at our next one. We have ammonium nitrate. Okay, ammonium nitrate. Now go ahead and practice that one. See if you can do that on your own while I write in some AQs here. What do you think this is going to turn into? Do you need to put that 4 and that 3 out in front? Or are they a part of polyatomic ions? Let's see what you came up with. You should have had it looking like this. Ammonium and nitrate. Remember, these are both polyatomic ions. The ammonium has a +1 charge, and then the nitrate has a -1 charge, right? And so it just looks just like that. Not too hard, no? Just got to remember the polyatomic ions. If you didn't remember that, it might get a little bit confusing. All right, let's try one more. This is going to be a pause and practice. So go ahead and pause it, practice this, see what you get. Okay, so let's see how you did. On this one, you should have had 2 Fe3 plus and 3 O2 negative. Now, we don't need that and there, right? This could have just been a plus sign. But I'm guessing that some of you guys might have missed out on the idea that this was an Fe3 plus. Okay, and you're like, well, how do I know what that charge is? Because remember that iron is in the group D elements, and the iron might be either a 2+ charge or a 3+ charge. And so you have to look at what was it when it was combined with oxygen. Remember that oxygen, in this case, oxygen is always a 2 negative charge, right, for the most part, unless it's part of a peroxide where it would be a -1. So oxygen's a -2, and I've got 3 of them. So 3 times a -2 is a -6. So when I'm asking what's iron's charge? Iron had to have a what charge, right? A plus something charge, question mark, in order for it to equal a +6. Why does it need to be +6? Because you want to balance the whole thing out to 0. Remember that? And so since I have 2 irons, 2 times what is equal to 6? 2 times a +3 is equal to 6, right? So we can solve that little question mark to know that that's a 3+ charge. And so that's why we know that this has got to be a 3+ here. Don't forget we want our AQs. If you didn't put your AQs there, make sure you put your AQs there. And we did take each of those subscripts and turn those into the coefficients because neither of these were polyatomic ions. And we wanted to say, hey, there's twice as many iron, 3 pluses, as there are iron oxides, and there are 3 times as many O2 negatives as there are iron oxides. Okay, so that's how we did that. If you guys have any questions, make sure to shoot those to me in the chat, and I'll go over stuff some more. All right, so let's look at what we get here when we talk about our dissolved ions, because we want to talk about the total number of moles in a product, right? And so when we look at K2SO4, for instance, the K2SO4 has a little 2 on the bottom here, and that 2 is indicating that there are 2 moles of the potassium ions once it is dissociated. Okay, and then the SO4, it doesn't have a subscript after it, you know, like it maybe could have had a 3 or something like that. No, it doesn't have that. So because it doesn't have a subscript after it, it just indicates that there's 1 mole of the sulfate ions that are combining with 2 moles of the potassium ions. Okay, so remember those subscripts are going to become the coefficient and basically tell us the number of moles. Okay. And again, it has to do with the single ions, a sulfate, which is a polyatomic ion. I would need to have parentheses on the outside of that to indicate that it had, you know, more than 1 mole of the sulfate. But in this case, there's no parentheses. So let's look at this one. It says, write a dissociation equation for aluminum chloride. How many moles of aluminum ions and chloride ions will be produced if 1 mole of aluminum chloride dissolves? Okay, so we're just trying to ask ourselves about the number of moles of aluminum and chlorine, right? Well, it's aluminum and chlorine, but there's a 3 after the chlorine, so we got to pay attention to that. There's not a 3 after the aluminum. There's just, you know, the imaginary 1 there, right? So if I start with 1 mole of aluminum chloride, then you're going to see that 1 mole of aluminum chloride turns into 1 mole of aluminum ions. Put an AQ after that, right? But then that 3 that was here on the chlorine, that tells me now that should be a 3 coefficient, which means that there's 3 moles of the chlorine. Should be an AQ after that. So 1 mole of aluminum and 3 moles of chlorine. Excuse me. Okay. So again, you can now tell about how many moles there are of a particular ion when you use this relationship as well. So the coefficient, the subscripts basically become the coefficients, and that basically tells you the number of moles. Again, if you have, again, this was all dependent upon this first starting part, right? That if you had 1 mole of aluminum chloride dissolving, then you could tell how many moles of chlorine and how many moles of aluminum you had. All right, now, if you guys remember, there was something called double displacement reactions, early on in the year, right? When first semester we talked about double displacement reactions. Remember that we had situations in which we had, like, you know, AD was going to the dance with BC, and then after they finished, they swapped dancing partners, and, you know, A was going away from the dance with C, and then B was going away from the dance with D, right? They swapped their dancing partners. Well, that was the double displacement reaction. And sometimes in a double displacement reaction, you're going to get a precipitate, right? That solid that falls out of solution. And what we're going to do is we're going to look at a solubility chart to determine the solubility of our products. Okay, we're going to look at our products and we're going to say, hey, what's the solubility of these things? And then if we have something that is insoluble, then we're going to say it's a precipitate. So for instance, let's say we start with magnesium bromide reacting with sodium chloride. Now, when we're done with that reaction, they may have swapped partners, right? So this is, you'll notice they have new dancing partners now, right? So they swapped partners, but yet, was there a solid precipitate that came out of solution? No. Both of these things are soluble, meaning they both completely dissolve in water, at least at these reasonable concentrations here, greater than 0.1 grams. And so you can say that these products are both soluble, okay, per 100 grams of water, by the way. And so if everything stays dissolved, we see no visible reaction. And so because we don't see a visible reaction, we're going to go ahead and write down NR. No reaction took place. Now, again, they may have swapped partners, but because we can't see it, we're not going to write down that we saw a visible reaction. So we're just going to say, hey, no reaction took place, okay? Now, here's an example of some that are soluble and some that are not. Look at this chunk of stuff that's at the bottom and the chunk of stuff that's at the bottom here. In these three, you notice we've got some interesting colors. We've got some green and some purple and some blue, and this one's completely clear. But in these two, we actually have some stuff that's stuck at the bottom. You can kind of see where that solid junk is at. None of these have anything solid at the bottom, right? There's nothing solid at the bottom. So all of these, we would say that there's no reaction. Okay, if these are the byproducts, we would say, hey, no reaction because we can't see a visible precipitate at the bottom. But in these two, we do have a reaction, and we have some aluminum chloride here, silver chloride here, and some cadmium sulfide here. Okay, that's what these two things are. They're saying that those are the insoluble products when you put them in water. And it's really cool, actually, like that cadmium sulfide. You put down two clear liquids, you put them together, and all of a sudden you get this really beautiful, bright yellow powder that kind of starts to settle out of it after a little bit. And so you have this precipitate that forms. That precipitate, we would say, is the insoluble product. Okay, the precipitate is going to be the insoluble product of this reaction. Okay, and so in these two, we would say, yeah, we do have a reaction taking place. Okay, so if one of your products is insoluble, then we say that it forms a precipitate, and so we say there's a visible reaction. Now, I want you to look on page 213 of your book, and you're going to see figure 1.3, and you're going to see that there are some rules. I think it's like 5 rules. You can add a rule to that if it's not in your book already, and it's this rule right here. Most hydroxides are insoluble. Okay, most hydroxides are insoluble. Now, you will definitely want to memorize these ones here. Group 1 elements combined with something else is always going to be soluble. Ammonium combined with something else is always going to be soluble. And the nitrate combined with something else is always going to be soluble. If you memorize those, that's going to make a lot of the problems a little bit easier because you're going to see the answer right away. Otherwise, you're going to have to look it up in a chart. I'm going to show you the solubility chart here in a second. But most hydroxides are insoluble. We'll check on which ones are not. But again, page 413, figure 1.3, you can look at that. It's a good table. It kind of, if you just look at those rules, it's going to help you find things pretty quickly. But this chart is the mother of all solubility charts, right? I'm sure there's even one more complex and amazing. But this one is really great for helping you figure stuff out and see if something's soluble or not. Notice that we have negative ions here in that column, and then we have positive ions in that column over there. So basically, you're going to need to look at the negative ions and the positive ions and see if you can find a certain combination. And then you look over here at this last column, not last column, but the second to last column, and you're going to be able to try to make a conclusion as to whether it's soluble or insoluble based upon the way that we connected things over here. Okay, so let's try one of these and we'll give you an example. Now you can find that in your classroom. If you go to classroom, I put that up, a solubility chart. So look under the unit with chapters 12 and 13. It's unit 7, chapters 12 and 13. You can find the solubility chart there in classroom. You can pull it up and then you can look at it. All right, so which of the following salts are soluble or aqueous in water? I've got 4 different solutions here. We want to take a look at these and we'll see which ones are soluble. We're going to use that chart. So we've got silver chloride, magnesium sulfate, calcium carbonate, and ammonium carbonate. And let's look at the chart and take them one by one. The first one is the silver chloride. Okay, Silver chloride. Is silver chloride soluble or insoluble? So what I've got to do is I've got to find the negative ion, right? So this is my negative ion. Find a chloride. Oh, here it is, right? There's chloride. And so if I take that chloride and then I come over and I take and look at my next column, my positive ions. What's my positive ion? It's silver. Oh, there's silver. Now, since I have silver with chlorine and I found the two combinations, now I can go and I can look at the next column. The next column says that it's insoluble, right? So I would signify this by putting an S there, that the silver chloride is insoluble. It's going to be a solid when it comes out of solution, all right? Or when it's created in the solution, it's going to be a solid precipitate that forms. Now, the next one let's look at is magnesium sulfate. Okay, so we've had magnesium sulfate. So we want to use our negative ion. Oh, there's sulfate. Now, don't use the British spelling with the PH here, all right? Unless you're from Britain, then you can. Otherwise, you're going to use an F there, S-U-L-F-A-T-E, okay? But that's sulfate. Now, I got to find magnesium. Is magnesium here in this list? Calcium, strontium, barium, silver, lead, radium? No, it's not. That means it must be on this any other cation list. Magnesium must be in this list because it wasn't in this list up above. And so then I come over here and I say, oh, well, it's soluble because I just follow that list across. And so then I would say, well, magnesium sulfate is going to be soluble. So I put an AQ after it if I were writing this one out, right? Let's look at calcium carbonate. So I've got to go to carbonate. Oh, yep, there's carbonate right down here. You see it? Carbonate. And now I've got to find calcium. Look to see if calcium's in here. No, calcium's not in there. That must mean it's in any other cation. That means it's, oh, low solubility, insoluble. So calcium carbonate, I'll just put it down here. Calcium carbonate should have an S after it because it's insoluble. Where'd it go? Come back. Okay. The last one is ammonium carbonate. Oh my goodness, look at that. Ammonium. We memorized that list, didn't we? We went back here. We were like, oh yeah, I memorized the group 1 ammonium is always soluble. I don't even have to look that one up. Okay, don't even bother because I got a great brain and I memorized it and I know this is always going to be soluble, so that's going to have an AQ after it. Okay, so it's not too hard, right? We just got to read our chart to figure out what we are doing. Let's look at a little practice here. Okay, so first we're going to do an example. Predict the products and state if this reaction will occur. So this is the type of the problem you can expect on a test. Okay, aluminum chloride, aqueous, plus calcium nitrate, aqueous, is going to produce what products? Remember, these are double replacement reactions, so we just need to swap partners, right? And so, sweet, I'm going to swap my aluminum with my calcium, and then I've got to look on my chart and see what I get. Okay, see if I get a soluble or insoluble one. Well, first of all, I can notice there's a nitrate here, and I've memorized, nitrates are always soluble. So this nitrate, when it combines with aluminum, okay, remember, because you're going to have aluminum coming over here, that's going to be soluble. Sweet. I don't have to look that one up. I know that. I memorized it. But now my calcium is going to be combined with chlorine. I'm going to have to look that one up, aren't I? So I'm going to have to look that one up on my table, and I'm going to say, all right, calcium and chlorine. Here's chlorine. Right? And calcium, let's see, look in here. Nope, calcium's not on that list. So that must mean it's any other, which means it's soluble. Okay? And so I can say, sweet, that one is soluble. And so that one is going to have an AQ after it. So both of these guys are going to have an AQ after them. So what would we say? We would basically say no reaction. Why? Because we can't see that reaction actually taking place. Even though this would be the way that they would swap if they swapped, maybe they are, but we don't see it. So we write no reaction. We say no reaction is occurring. Make sense? Okay, so it's your turn. All right, so you are going to do this one. So a little pause and practice for those of you on video and see what you guys get on this one. Okay, welcome back. How did you do? Let's see. So we had to swap our cations, right? We had to swap our potassium with our sodium. And so that means we were going to go with a sodium hydroxide and a potassium carbonate, right? So you had to combine those two together to get the potassium carbonate. Now you'll need a 2 there because carbonate had a -2 charge. And you'd need the sodium hydroxide over here, right? Well, let's look at our chart again. Here's hydroxide. Now, remember, we told you to write down most hydroxides are insoluble. However, look at the ones that are soluble. Look at this, sodium right there. So sodium hydroxide is soluble, right? The other one we were looking at was the potassium carbonate, right? So we went to our carbonate, which was there, and we were looking for potassium. Oh, there's potassium. Oh, look at that. It's soluble as well. All right, so for that one, you should have gotten that this reaction was an NR, right? Because they're both soluble, they both would have been aqueous. So we don't know for sure that a reaction takes place, so we're going to say NR. Okay, thank you. So the next one, okay, let's try this one. Barium chloride and iron 2 sulfate. All right, so another little pause and practice. See how you do on this one. All right, so welcome back for this one. We've got barium going to be combined with sulfate, right? So we've got a barium and a sulfate. Now sulfate has a -2 charge. Barium is in the second column, has a +2 charge. So that's just BaSO4. And then iron is now going to be combined with chlorine. And since there's 2 chlorines and iron had a +2 charge before, we're going to keep it with a +2 charge now. So we want to look at barium and sulfate. All right, let's look at our sulfates. Oops, that's not sulfate. That's sulfite. Here's sulfate. And we want to look to see, oh, there's barium, right? You see it? Barium, sulfate, ooh, insoluble. Okay, so back to that. This barium sulfate is going to be a solid. Awesome. I have a reaction here. And now let's look for iron chloride. And so if we look at chlorine, go back to our chlorine here and then look for iron. Nope, iron's not on that list, so it's any other. Therefore, it's soluble. Therefore, we can say that this one is aqueous. Yay! So this reaction does take place, and this is going to be our precipitate. Barium sulfate would be our precipitate in this case. Awesome. All right, so let's talk about ionic equations. Okay. A total ionic equation versus a net ionic equation, those two things we want to make sure that we are clear with our definitions. Total ionic equations are going to include all of the aqueous, ionic, okay, or soluble compounds that are represented as ions. So we want to make sure that we make every single ion an ion. Okay, if it is soluble by itself and it's not a precipitate, then we need to represent it as an ion. Anything that's insoluble or a precipitate, okay, we need to represent by its complete formula. Now, if it's a precipitate, you can also have liquids and gases that would need to be represented by its complete formula as well. Okay, so either solids, liquids, or gases in a total ionic equation need to have their complete formula. So for instance, if we were doing that one that we just did and we had barium sulfate, we would want barium sulfate, the whole formula here, to be written out. Okay, we want the complete formula. But on the left side of the reaction, we'll see on the left side of the reaction, we would have had a barium 2+ ion and a sulfate 2- ion. Okay, and so that's kind of the difference. Like if they're not together, then we write them as their separate ions. But once they are together, we put them as a complete formula. So for instance, if we were doing this formula here and we had a reaction of sodium chloride and silver nitrate, you can see that we have the sodium chloride plus silver nitrate. Both of those are AQ. And then on the right side, on the product side, we have silver chloride is now going to be a solid, right? So this is a precipitate. And so this means that we are going to have to represent, when we write our total ionic equation, we'll have to represent silver chloride as a complete formula. So this is how we do it. Not too hard. We just take each individual ion. It's detail. Okay, we got to do a lot of detail, a lot of work here. But we have to separate every little ion out, but it's not hard. The NaCl becomes Na plus AQ plus Cl minus AQ. Okay, and then we do a plus, and then the silver nitrate becomes Ag plus Aq plus NO3 negative Aq, right? So we have to break everything up into its separate ions. On the right side of the equation, where it's a product, then, like I said, we keep the things that are now new products, whether they be solids, liquids, or gases, the new thing that's formed, we keep that together as a complete formula. But then the Na plus Aq and the NO3 minus Aq, they stay separated. Okay, why? Because they're still separated as little aqueous ions. They're surrounded by water. These little ions are surrounded by water, right? And so the AgCl isn't separated anymore into the Ag and the Cl. They combine together. They precipitate it out as a new solid. So this is a total ionic equation. This one down here at the bottom, okay, this was your chemical equation. That's just your regular chemical equation, right? This is a total ionic equation, okay? And it's got all that work. It's not hard. It's just a lot of detail, and you just got to do a lot of writing, okay? So let's identify a couple parts to this. First thing we want to identify is the spectator ions. Things that are the same on both sides of the reaction. There's an Na plus Aq and an Na plus Aq. There's an NO3 minus Aq and an NO3 minus Aq. They're the same on both sides of the arrow, right? Look at your arrow, see what's the same on both sides of the arrow. The things that are the same on both sides of the arrow, we call those spectator ions. And basically, we're going to cancel those out because they're just spectators. When we write our net ionic equation, that's this next big term here. When we write our net ionic equation, we cancel out our spectators and we look at what's left. So look at what's left. Here's our chlorine, whoop, right there, right? Here's our silver, whoop, right there. And here's our silver chloride, whoop, right there. Everything's better with sound effects, don't you think? All right, so this is our net ionic equation. It's taking your total ionic equation and taking all the spectators out of it. And so now I have chlorine negative minus Cl minus Aq plus Ag plus Aq gives you AgCl as a solid. And that's how you do a net ionic equation. All right, so we've got total ionic equation, spectator ions, and net ionic equation. Not hard, just a little detail. All right, so this is some practice. Now I'm going to show you this one, and then I'm going to let you do the next one. An iron 3 nitrate solution is combined with sodium hydroxide solution. So first of all, we got to come up with a balanced formula equation, right? So iron 3 nitrate, iron, right? And it's nitrate, but it's iron 3, which means that I have a 3 plus charge on my iron. Got an extra little line on my E too. That 3 plus charge is going to crisscross and come down to the nitrate, right? So this is iron 3 nitrate. And it says it's in solution, so that's AQ. It's combined plus with sodium hydroxide, NaOH. And this is a solution as well, AQ. Now I've got to predict my products. Well, my iron is going to end up going with my hydroxide. It was a 3 plus charge over here. Let's keep it a 3 plus charge over here. So that's going to be 3 hydroxides that need to balance that out. Plus my sodium and my nitrate. Now remember, we memorized that nitrate is always AQ. Now we probably better check our hydroxide, huh? So let's check our chart. And if you guys have your charts available, you can check those charts, but I'll go ahead and zoom back on it. Space back a few. Excuse me while I go back. And we're going to look for the hydroxide. Woo, too far back. Got to look there. Come on, buddy. All right, so here's our hydroxide again, right? And we want to look for iron. Uh-oh, no iron up there. That means it's any other cation, which means this has insoluble. Okay, so let's go back. Hopefully I won't go too far this time. Taking my time, taking my time. Yeah, I went too far. Wouldn't you know? Okay, so now we have the determination that that is a solid. Okay, now we got to break it up. Okay, that's our balance. Oh, wait, is it balanced? It's not balanced nitrate. Got to put a 3 in front of that. And then that means there's going to be a 3 in front of that. All right, now I think we're balanced. All right, now I've got to do a total net ionic, or total ionic equation. Got to break everything up. So this is where you got to do the work. Ladies and gents, it's a lot of work, but here you go. Fe, 3 plus AQ plus 3. Notice I've taken this 3 and bringing it out in front. NO3 minus AQ plus 3 Na plus AQ plus 3 OH negative AQ. Notice that this 3 applies to both the sodium and to the hydroxide. Okay, it's here and here because it's the coefficient that's out in front. The subscript only applied to the nitrate here, right? Gives me, hey, I can keep this all together. Yay! FeOH, okay, iron 3 hydroxide, plus 3 Na plus AQ plus 3 NO3 minus AQ. All right, now, remember it says that we're supposed to look at our spectator ions, right? So which ones are our spectator ions? If they're the same on both sides, we got to get rid of them. 3NO3, 3NO3. Boom, boom. Yeah, we can get rid of that. Boom, boom. That's spectator. 3Na plus, 3Na plus. Yeah, ba-boom, ba-boom. Those are the same. We can get rid of them. What's left? Okay, get rid of our spectator ions. What's got to be left is got to be your net ionic equation. Fe, 3 plus AQ, excuse me, plus 3 OH negative AQ gives me FeOH3 as a solid. All right, there, doing you a solid right there. You've got your net ionic equation, and that is how you would do that problem. Okay, so again, it's not hard, it's just detailed, right? A lot of detail. Okay, so this is the one I want you to practice on your own. And so we're running out of time, so we're gonna do a little pause and practice, and then we're gonna finish up our concept, right? So that's like a pause and practice. Practice that on your own. And I'll come over the answer for that. And let's talk about this last little term and then look at our objective. So our ionization. I said this at the beginning of the chapter, but ionization is where you take a molecular compound and you turn it into an ion, okay? So if it forms an ion in solution and you start with a molecular compound, but it now forms an ion because it's doing some reacting with the solvent, it somehow reacts with the solvent, then we call this ionization. So for instance, hydrochloric acid, when you put HCl in water, the HCl bond is very polar. The water molecules can pull it apart. And because it pulls apart into its positive and negative ions, because it's so polar, then we call this ionization. Now, this hydrogen ion, this positive ion, is unstable. Means that it immediately reacts with water and forms this new little guy, H3O plus, called the hydronium ion. And we're going to learn about this in our next chapter. But this hydronium ion is what basically is responsible for what makes an acid. So you heard me say hydrochloric acid, right? Well, the hydrochloric acid, the hydrogen breaks up and combines with the H2O to make H3O plus, a new ion, and that's called the hydronium ion. And the number of hydronium ions is actually what determines whether or not an acid has a certain pH or not. So that's ionization. All right, well, we're just out of time, so let's just kind of make sure you can determine the difference between dissociation and ionization. And all right, so briefly, I want to talk a little bit about electrolytes. Again, this is review, but it's kind of nice to bring it back around to dissociation and ionization. Now that we've talked about those concepts, these electrolyte concepts are good ones to reinforce here, because we talked about strong and weak electrolytes before. Now, strong electrolytes are those electrolytes which are able to completely dissociate or completely ionize in solution. So they are going to have lots of ions because they completely break apart. All right, so you can just imagine the water going around and surrounding every single little ion, right? A weak electrolyte is only going to partially dissociate or ionize. In other words, the water's going to get around some of them and kind of, solvate or kind of go through that solvation process around some of the ions, but not around a lot of them. So it will do it with some, but not all. And so you get few ions forming in these solutions. And so that's what makes a weak electrolyte. It doesn't conduct electricity nearly as well as a strong electrolyte. And now that we've talked about dissociation and ionization, it kind of connects this concept a little bit better. So what do we look at when we look at strong electrolytes? We're looking at sodium chloride, for instance, or silver chloride. Now, notice the difference between sodium chloride up here, right, versus silver chloride down here, that the strong electrolyte is not necessarily going to mean that it completely dissolves, because there's still some stuff undissolved at the bottom, right? You can see these little chunks down here are the undissolved portions of the silver chloride. So the silver chloride might be slightly soluble or insoluble per se, at least at this point, once I've gotten so much in there, but it doesn't mean that it's not a strong electrolyte. It can still completely be surrounded by water for the amount that actually can dissolve. Okay. The weak electrolyte, however, has some things that stay together. So notice here that hydrogen fluoride has some parts that are stuck together, but some parts that are not. This is a fluorine all by itself, and it doesn't have the hydrogen attached to it, right? So this HF did not get solvated, right? It did not get dissolved or ionized in this case, right? It did not get separated out where the hydrogen is being surrounded by water and the fluorine is being surrounded by water. This one did. So this fluorine ion did get solvated, and the hydrogen went to be a part of this water molecule and become an hydronium ion. But this one didn't. So this is a weak electrolyte because only some of them will get solvated. And here's another one that didn't get dissolved, right? And so this is why it's a weak electrolyte. Now, a non-electrolyte, if you remember, we talked about sugar before. This is sucrose, and sucrose does not become an electrolyte even though it is solvated, okay? So just remember that it can still be dissolved and can be completely surrounded and it not be an electrolyte. Why? Because it doesn't have a charge, right? There's no ion here. So in order for it to become an electrolyte, it has to have a charge or it has to have an ion. And so these two models down here, this one and this one, kind of give you some differences. Here they're showing you that you can still have a strong electrolyte without having everything dissolved. And here you can see that everything can be dissolved and you still have no electrolyte because there's no charge. All right, so strong electrolytes and weak electrolytes with a couple of those other exceptions to them. Let's go through our objectives here. We can now write dissociation equations. We can write total ionic equations, and we can identify spectator ions and write net ionic equations. Okay, so I skipped a little bit about electrolytes, but we've kind of talked about that already. Given an ionic compound, I can write a dissociation equation to represent how the ions separate when the compound dissolves. Given a precipitation reaction, I can use solubility rules to determine which product will be soluble and which will precipitate, and I can represent precipitation reactions with total and net ionic equations. Okay, all right. God bless you guys. You are dismissed. Have a good one.